Hello, everybody. Today we're going to talk about the general discrete probability distribution. Let's get right into it. We have a tab called Discrete. And in here, I have three charts and some questions I'd like to go through on each one of these charts. Let's start with chart one. Chart one, probability distribution for damage claims paid by insurance company on collisions. All right, so let's go inspect the chart. First thing before I answer any questions, I look at the chart to see what the chart says. Well, the chart says the following information. What we have is we have the payment, how much we've paid out if we're the insurance company, and the odds of that payout. So 85% of the time, a claim comes in with no payment. 4% of the time, there'll be a claim coming in with $500 payment. 4% of the time, there'll be a claim that comes in on collision that's $1,000 in payment, so on and so forth, all the way up to 1% of the time we see collisions and the payment on the collision is roughly $10,000. So the first question right off the bat, if we label these A, B, C, D, question A, WITP. In future videos, you'll hear me say this all the time. What is the probability? So what is the probability the payment will be 5,000 or less for a random collision? Good question. The answer, which we'll put over here, the answer is all about reading the table. All right. They want what is the probability the payment will be 5,000 or less. So look at here, the payment 5,000 or less means all of these highlighted numbers I just highlighted, right? $5,000 payment, $3,000 payment, $1,000 payment, $500 payment, and $0 payment. What are the odds? Well, the good news is we have the distribution of the odds to the right. And this distribution, when I add these numbers up, will give me the odds of a payment being 5,000 or less. The good news, because my chart's so small, I'm actually going to use the complement. I could add these numbers up. Instead, I'm going to add up the chances it's going to be over 5,000 and then subtract from 1 because I don't want over 5,000. Notice, over 5,000 is actually 2%, right? That means to be 5,000 and under has to be the complement. And so my answer here will be 1 minus 0.02. So to activate the calculator, 1 minus 0.02. And so I expect the probability for my answer to be 98% chance. What is the probability of the payment be 5,000 or less? A 98% chance. Why is that? Because what we have here again is there's only two items above 5,000 and their odds are 2% in total, which means there's a 98% chance that it'll be 5,000 or less for the collision total. Excellent. By the way, what I like to do is I like to run a quick check, and I usually do it before I actually start any questions. I like to make sure the probability distribution makes sense. And that's where I use the sum command if I have all the numbers. The sum command in Excel, if you're in Excel, what it will do is it will add up all the numbers that you scan in. In this case, I want to scan in all those numbers, and it adds up to 1. This is an important check to me. If it did not add up to 1, I'd wonder what is hiding, what information is lost. It's really a check for me to make sure I built the probability distribution correct. Now, where do these distributions come from? Collecting data. What I imagine is this company here, let's say they've collected 100 claims, or I should be careful, these claims here, and it could be these claims here don't involve any collision payment, okay? So there's 85, I imagine 85 times out of 100 that there was no collision payments. There was 4 times out of 100 collisions that there was a $500 payment, so on and so forth. These probabilities really give me an idea of what's happening in terms of this insurance company and collision payouts. Again, when I see 0.85, I think, there's 100 collisions. Let's say there's 100 collisions in a month. I realize that 85 out of 100 will pay out 0. I realize 4 out of 100 will pay out $500. That's what these represent. So I get an idea of how many out of 100 collisions would be in each payment bracket. It's important this adds up to 100 for the fact, if not, there is a data file I'm missing, a data set that I'm missing. There's a value missing. If it's over 100, that means I've double counted something, and you can't have that either. It's very important that this number adds up to 1. It checks that we have a probability distribution, and we want that. All right, part B. What is the probability the payment will be more than 500? Well, more than 500, the great thing with the chart is you would just, these are the numbers more than 500 right here that I've highlighted, and their associated probabilities are here. And so I can quickly scan those and add those up, 7, 8, 9, 10, 11. So I see 11%. All I did was I added them up, and I see my answer is 11%. Why did I write that in percent this time? Just to show you can go back and forth. You have to understand which format you want the answer in. What format do you want? Do you want decimal or do you want percent? That'll be given by the question. You have to make sure you understand that. So what we did here is there's 11% chance that we're going to pay more than $500. How do I know? Another way to look at it is complement. So 500 or less is 89%. I can see these two numbers add together 89%. The complement would be 11%. Complements are a great thing in probability distributions, especially when you have a large chart. These are not large charts. All right, these are small charts. You can quickly add up in your head if you'd like, as I'm doing. All right, so two big questions come from probability distributions. That is, what is the expected payout? All right, what is the expected payout this company would expect to pay out? Well, if I want expectation, I need to know a formula for expectation. The good news, I have that. So if we click to our formula sheet and we know we're a discrete random variable, then the expected payout, that is the mean payout, is the following formula. It's the sum from 1 to I of xi times the probability of x being a certain xi. So what does this formula mean and how do we utilize it? Well, xi would be each occurrence, that is each action, each payout. The probability of the payout, well, that has to be given from data collecting, which we have in this chart. We have the payment. You can call that your xi. And your probability of that xi is right next to it. So what we can do, according to the formula, is we're going to add up. That's what this right here represents, by the way. This symbol means to add. This sigma means to add. We're going to add from 1 to n. What it means is we're going to add up from 1 down to the number of items we have in this chart of x times the probability of x. All right, we could do that. We could do x times the probability of x column because we know how to utilize Excel. What does it mean to be x times probability of x? Well, it truly means x times the probability of x. And once you have written a formula correctly in Excel, we can copy this formula down and it just fills in the pieces. If you're doing this by hand, obviously you just have to understand for each and every payment type, you're going to have to do x times this probability. You have to do x times this probability, and that's what this column represents. You have to do x each payment time times the probability for each payment type. That's why the xi, to represent an index of how many times you have to do it. Now, if you sum this column up, you're doing that sigma in the formula, and this is actually the average. So the average would be $430 per person, or it shouldn't be per person, per collision. So that's the expected payout, is a $430 per collision. Again, expectation by our formula is the summation, add up all the occurrences of xi times their probability. And that's what this column represents. Xi, this is probability, and this is the multiplication of them. So we add that up and you get your expectation as we are looking for. So this number is invaluable. This is the expectation. So we expect in this company to pay out $430 per collision. Now, why do we care about that? Well, let's put it in practical sense. Let's look at part D. What premium should we charge per person then to break even? The answer is part C. If we charge $430 per customer, then in the end, we should break even at that charge. So if we charge the average, we will break even in the end because, again, the per person collision payout is $430. If we want to break even, we just set the premium to be $430. If you want to make a profit, just charge over that amount. How much should you charge? That's left up to the company and their decision. All right, on to chart 2. What I would ask you to do right now is pause the video and see if you can answer the 3 questions in chart 2 without me prompting you, or at least A and B. Sorry, I apologize. At least A. We have not discussed the standard deviation yet. So try to do part A without me. All right, we're back. So how would I find the expected bonus amount? Again, I like to look at my chart, see what we're talking about. So what we have is a local firm, ad firm, whatever type of firm, marketing firm you have, and the employer is going to give out bonuses based on performances, job performances, quarterly or yearly job performances. And the payouts are $10,000 if you get an awesome, $6,000 for good, $3,000 for fair, and you get nothing if you're a poor job performance. The odds of these have been carefully collected. Why? Well, not why. How? Easy. Again, let's imagine you had 100 employees. You would just look at them and you'd look at their previous past performances and typically say 15 out of 100 are awesome, 25 out of 100 are good, 40 out of 100 are fair, and 20 out of 100 are poor. First thing I'm going to do is run my check. I'm going to make sure that I have not missed anybody or double counted anybody. And it looks like my check is good. My check is 1. That tells me that I do have a fair probability distribution. All right, so now we want expectation. Well, from the previous example, expectation is found by summing up each outcome times its probability. So first, I have to find each weighted outcome, as it's called. That is, you take the outcome times its probability, and that's its weight. We'll use that formula a few times to get each and every individual weighted outcome. So 10,000 times 15%, 6,000 times 25%, 3,000 times 40%, and 0 times 20%. Not adds, equals each one of these numbers respectively. Expected value is the sum of these. So I expect the payout for the bonus to be a typical 4,200. So I know, or I typically think, and I'm trying to give me a little bit more space, so I'm going to insert here. There we go. For A, I know the typical payout would be a bonus of 4,200 per employee. That's what I'm expecting to pay out per employee, 4,200. All right, cool. That is what we call the mean, the average, the expected. If we're looking at a regular data set, after expectation, the center of the data, you want to find the spread per person spread. So if I had 2 random employees, what is the average difference between them when it comes to bonus? That's called the spread. I notice I had the word bonus spelled wrong. All right, so in part B, what is the standard deviation? Well, the standard deviation is very similar to the standard deviation formula that we have up here. we're going to utilize the variance. So we're going to utilize the variance formula up here. But we're going to switch it to a probability distribution formula. And the variance formula, sigma squared, is the summation of xi minus mu squared times the probability. So we're going to write this in Excel. If you have to do it by hand, just understand you just found mu, right? You just found the average, 4,200. So if I was to find the spread, what I would do is take each outcome minus the average squared, because if you don't square, you get 0 all the time. We talked about this when we talked about variance up here before, and that's why the variance up here is squared. And to weight it, we multiply by the probability. So let's see this in action. I'm actually going to type this whole thing in Excel right in one line, the x minus mu squared times p, because then I could just add up the column. When I see sigma in Excel, I know that means to add up the column. First, I have to get each one of these items. So I have to take x minus mu squared times probability. Great thing about Excel, we can do this all in one step if you're careful. So to find variance, I need to do again x minus mu squared times p. That's what I have to do. So let's do it in Excel. You can do it by hand also. You have to have a parentheses. You have to have your xi, which is your individual payout. Take away the average, which we found, 4,200. Square it, and then multiply it by the probability to weight it accordingly. At any time you get lost, you should pause and think about what I have done, how the formula plays into this. If you need to, take a snapshot of the picture, because I'm just utilizing these two formulas over and over in this lecture. The mean and the variance. Notice I'm using Greek letters. They're Greek because I have all the items in my data set, which means I have a population, and so I can utilize the Greek letters because I have a population. I do not have a sample here. I have a population. All right, back to here. You wrote the formula. Nice. And so then I just go, I got to be careful. One of these numbers does not move. That is the average. So I have to absolute reference the average. Please look up absolute reference if you're wondering about those dollar signs. Pretty much what it means is that 4,200 is a constant in this equation. That constant I never wanted to change. All right, so I bring this down, boom, 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 and I get the individual pieces. By summing up, I get the variance. So this is the variance. And remember, this would be the bonus amount squared. That's really what this is the bonus amount squared. And I don't understand how to say square money. All right. So what we do to find the standard deviation, we square root the variance. And so this would be the per person spread. That needs to be very importantly clear. All right. This is the per employee spread when it comes to bonus. So I expect a differential between employee of $3,155, 95 cents if you care. So again, I expect per employee, so if I grab two random employees, their average difference would be about $3,155 at this marketing firm. So I got two numbers. I have the average, what is the typical, if I grab one employee, what is the typical amount per employee, 4,200. And then I have the typical, if I grab two employees, what is their average differential? Their average differential, the standard deviation, the spread factor, right, would be $3,155 per person. And put a dollar sign on that. Boom. If you wonder where the dollar sign is, it's on the home menu, dollar sign. All right, so part C, last part. If the company has 30 employees, what is expected total amount paid out? Let's get to the practical, right? We did these two questions. Great, mathematical. What is the importance of understanding the mean and the standard deviation? Well, so you can answer questions like part C. If the company has 30 employees, what is the expected total amount paid out? So that way the employer can make sure he or she has enough money so they can pay out the bonuses for this year. I'm pausing because I want to give you a chance, or you can pause the video to see if you can come up with the answer. Welcome back. The answer would be 30 times the per person number, right? It'd be 30 times the per person number. So this would be the total amount paid for the bonus. Again, think about it. If it's $4,200 per person, that's the expectation, and you have 30 employees, you multiply the two numbers, and you'd expect to give out, let me put my comma in there, $126,000 in bonuses. So we got to make sure that we do have that number somewhere in our account to make sure we can pay off the bonuses for this quarter, for this month, whatever this performance measurement is out of. Excellent. So we have one more to do. And before I do this one, I would ask you to pause the video again. And now that you've learned everything there is really to know about a general distribution, try it out. All right, we're back. So a general distribution, there's usually a few typical questions. You know, how do you read the chart? What's expected? What's the spread factor? And really the use of it. Why do we use it? Why do we look for it? So, all right, chart 3, what is it? It's a prize wheel. It's a prize that happens in the flyer. So customers get a flyer in the mail from their favorite company. In there is this code. You come to the store, you cash out, the code would tell you what you get. So if you have the winning code for the car, you'll get a car that's worth $20,000. There's only one winning code for that. The trip is a $5,000 trip. There's only one winning ticket for that. Gas card, we get 100 of them. And we get the $100 gas card. I should be careful. It's a $100 gas card with 10 winning tickets. And then there's 49,988 other tickets where you get a $5 shopping card you could use for future purchase. So first I'll put these in dollars so you can see these are dollar amounts. So again, what do we have here? We have a car at $20,000, a trip, $5,000, a gas card, and a shopping card, and the frequency at which they can be won. One chance for the car, one chance for the trip, 10 gas cards, and a $5 shopping card, just so that way it gets people into the store. All right, so the question would be, there's a bunch of questions, I apologize. The first question, as you see here, part A, how many sales flyers should this company distribute? The answer revolves around a check I'm going to do. That is, I would love to know how many winning tickets we're giving out. And since we're giving out 50,000 winning tickets, I would say we'd want 50,000 flyers. That way, at least everybody gets a prize, right? Especially if you wrote in there, minimum prize is a $5 shopping cart. So then you definitely want at least 50,000, not at least, exactly 50,000. If everybody's to win, then you want 50,000. If you want some non-winners, we would just have to augment this set with a non-winning ticket, the value being 0, and the number we have out there. But right now, we're going to say everybody wins something. Everybody wins a minimum, a shopping cart. That's why my check, how many flyers should I deliver to the customers? I'm sorry, you couldn't answer that until I articulated better. In this case, we want 50,000 flyers to ensure everybody wins. To ensure everyone wins. And that's one way to ensure everybody wins, is by making sure we have enough flyers so everybody could win. Excellent. All right. Now, what is the expected value of the price per customer? Great question. The grocery store would like to know what is the expected price give out per person. The reason I'm pausing is because I wanted you to see the difference between chart 1, chart 2, and chart 3. Chart 1 and chart 2, we were nice. We had the probability distribution already set up. We don't have that yet. We will soon have that. But notice we don't have the probability column like we did in the previous chart 1 and chart 2 examples. So how does one create this probability distribution? Well, think about probability. What is probability defined as? Probability is defined as success divided by total. So the odds of somebody winning the grand prize of a car is 0. Not true. First of all, we don't have enough decimals. So we need to go up here on the home menu, make sure you can increase the number of decimals. And I'll have to increase the width also. And there it is. There is the odds of winning the car. 1 out of 50,000. That's not a big chance, but it's still a chance. It wasn't 0. All right, let's see what the odds are of winning the trip. Should be the same, obviously. And we'll have to, for each one of these, we'll just make sure we have the same number of zeros. Good, for consistency. Equals, what's the odds of somebody winning a gift card for the gas card, the $100 gas card? Success, there's 10 of them. Total, there's 50,000 cards given out, or 50,000 flyers with these codes given out. So again, notice the first 3, not much of a chance of winning them. So what's the chances you're going to scratch off, or whatever this type of winning prize is, this code gets scanned in, what's the chances you win the shopping card? Well, look, that's how many shopping cards were given out of the total. So it's an overwhelming 99.976% chance, 99.976% chance you're going to win the shopping cart. Okay, once we have the payout and the probability, we can create expectation. Remember, expectation is the sum of the xi times the probability of that xi. I've been utilizing Excel. You could do this all by paper. You would just take your x and multiply it by its probability. You would just take the x and multiply it by its probability. You would write all those down, and after you have all those down, you can sum that up. And the summation of that would be the expected value. So I know the expected value of the price per person is $5.52. $5.52. So $5.52 per person payout. Excellent. Now, if you wonder what these are, this again is our famous check right here. Probability should add up to 1. And so then our expectation, which I've been labeling in orange, is 5.52 per person. Okay, so we know the typical person will win $5.52 when this game has been played. Let's insert. Let's add one more column. That way I don't have to write this again. I'll just copy this down. There we go. We're going to utilize this formula again to find the spread, because part C is the spread factor. If I have 2 customers in line with 2 codes, what is the average difference between their prices? Let's check it out. By the formula for standard deviation, or sorry, for variance here, that's what we're finding in this column. Recall, this is the variance column. I'm going to take x minus mu, so x minus the average, good thing we got the average now, squared, times the probability to weight it accordingly. Please note, I did not write this formula totally correct. I now am going to absolute reference H26, that is the mean, because the mean does not change in the formula when you utilize variance formula. When we add across, we get this new measurement called the variance. So that's the variance. That would be the squared price per person, the squared payout per person. Don't want that. So we square root, and in fact, I'm not going to do it here. I'm going to do it over here. We square root the variance to get the standard deviation. And so that tells me there is a $92.18 difference per person for prize. That's the typical per person prize differential. So two people standing in line, I would expect with the coach standing in line, I would expect a difference, a typical difference of $92 per person. Remember, spread helps us understand what is an outlier, what is not an outlier when it comes to distributions. We know the center, the typical person, will get a $5.52 prize. We know the spread, the difference between two customers, is about $92.18. So now we come to the real life question. All of them are real life. I like to know what is the price payout per person. I'd also like to know the difference between customers so I know what's expected and what's not expected. The spread is very important to me. So it kind of tells me what to expect when people bring in codes, because maybe people are cheating. I'd like to know if people are cheating. Spread is very, very important when it comes to understanding reliability and validity of these distributions. All right, D, is this a good promotion? Well, that's really up to the grocery store, the market. Is this a good promotion to use? I think so, because I'm looking at this. So what? We're going to give out $5, pretty much $5 per times 52 per person. But I guess I got to be careful. When this would be great is if we attract more than 50,000 people because of the promotion, or if we can't attract more because that's all we're giving out, if the customer spends more than $5.52. All right, if these customers come in, that's the key to really why this is a good promotion or not. What we could do is we'll track each person that comes in and uses a code. If that person is spending, if we knew, first of all, there's two things we'd have to know: what they typically spend and what they spend today. If they are spending more than they typically spend because of this promotion, we got them out there. We got them out there out of their routine. We got them to spend more than they typically spend. And if they spend more than $5.52, then yes, this is a great promotion because we got these customers in and they spent more than they typically spend, which means this is a great promotion. If in the beginning I added a column here for non-winners, this might be where I state that if we attracted more than the winners, then it's overall a great deal for us. So I'm going to hold back on that statement in my answer. I like this statement better for this example because we're only giving out 50,000 flyers. If we gave out more than 50,000 flyers, there's a chance, because we attract more than 50,000 people, that we could definitely make out on this deal. If the customer spends more than $5.52 over their typical amount, so they came in on a non-typical shopping day, then this is perfect. We got them to come in on a non-shopping day. They're spending more than $5.52, the average. This is awesome. We're making out hand over fist on this promotion. That won't be known until the promotion is done and we can track what we typically get and what we got because of the promotion. That is, what we typically get means what the grocery store typically makes per person prior and during the promotion. That's really what I'm looking for, is what is the typical sales versus what is the sales when the promotion is going on. See if that increase is worth that $5.52 we're giving out per person prize. All right, guys. Thank you so much for watching my video. Stay tuned for more.